Okay, here's part 2 of the lecture on sound boxes. Specifically, we'll take a look at the 2 lecture examples associated with sound boxes. Go ahead and pause the film right now and copy down the first of those 2 problems. Okay, the first of those 2 problems has to do with this demonstration that you saw earlier. With this demonstration, we can actually use this demonstration to measure the speed of sound. Okay, here's the problem itself. The tuning fork has a fundamental frequency of 384 hertz and is used to create a standing wave in a closed pipe. At what length will you hear the n equals 0 antinode? So once again, let me perform the demonstration for you, explain it, then we'll calculate out what it is that we're supposed to find, and then I'll briefly explain at the end how we can use this demonstration to measure the speed of sound. It would have been a lovely mini lab exercise for you. At any rate, however, this right here is a frequency, that is the fork itself, has a frequency of 384 hertz. Give it a whack. And then like so, that right there is the n equals 0 antinode. So what we're asked to calculate here is right here the length of the sound box itself, the length of this resonant chamber. Okay, initially at least, it's a little bit difficult to picture exactly what's happening in this demonstration, so here's essentially what it looks like. All right, so right here is the graduated cylinder like so. And then right here is the water line. Okay, and then we have the metal cylinder immersed into the water like this. Like so. And then right here is the tuning fork itself, which has a frequency of 384 hertz associated with it. Okay, while I was drawing up the tube, you didn't hear a nice, loud, clear tone. However, at just the right length L here associated with the chamber, then you have the n equals 0 antinode appear at the open end of the pipe. What that means is that the sound wave itself within the chamber, there is 1/4 of a wavelength present. That then looks like this mathematically. And then half a period later, it oscillates to here. So right here is a node at the water line. That's the closed end of the pipe, if you will. And then right here at the open end, this is where we now have the n equals 0 antinode appearing. Okay, now once you understand this, mathematically there's really nothing to this problem. We just have to work with the fundamental frequency equation for a closed pipe. Recall what that looks like. The fundamental frequency is the quantity V over 4L. Okay, so we know what the frequency is, and then what we do is we have the speed of sound V, which is 343 meters per second, and then we just calculate the length, that's all. All right, so let me just cross multiply here and solve for L. That's just V over 4F, and now let me just go ahead and calculate it. All right, so 343, and then divided by 4 times the frequency of the fork, which was 384. And this comes out to be a length of 0.22 meters. So that's 22 centimeters. So 22 centimeters on my ruler here. There is a ruler, by the way, that is taped here to the side of this metal pipe. 22 centimeters is down here like so. So once again, to demonstrate this, go ahead and immerse it in like so. And now draw it up so we hear the antinode. It's about like so. And then sure enough, this distance here is about 22 centimeters on the ruler. Okay, here's how we can then use this demonstration to measure the speed of sound. It's basically the same problem, just a little bit backwards. So in order to measure the speed of sound with this demonstration, what you would do is you would take forks of known frequency, locate the n equals 0 antinode as I did, and then measure L. So then therefore, if you know what the frequency of the forks is, and you measure the lengths L, then the only unknown is the speed of sound V, and it's actually easy to find. As I said, it would have been a lovely mini lab exercise for you. Okay, go ahead and pause and then write down the second problem here for this lecture in your notes. I'm going to go ahead and erase the board and put it up on my screen. Okay, this is a successive harmonics frequency problem for a closed pipe or an open pipe in this case. It's similar to one of the easy standing waves on a string problems that I did in a prior lecture involving successive harmonic frequencies. As you'll see, however, the closed pipe is a little tricky to work with mathematically. Okay, so here's what we're given. So an organ pipe resonates at 264, 440, and 616 hertz, but not in any frequencies in between. So let's say the frequency number 1 is 264 hertz. Okay, let's say the frequency number 2, that's 440 hertz. And then we have frequency number 3, that's 616 hertz. So this organ pipe resonates at these frequencies, but not at any frequencies in between. Is the pipe open or closed? Let's first of all assume that it's an open pipe. So if I make the assumption that it's an open pipe, the harmonic frequencies are governed by the following expression, NV over 2L. So just like I did in one of the standing waves on a string problem in the earlier lecture, let's go ahead and write this expression for, say, the first two frequencies. Let's say that frequency number 1, F1, is NV over 2L. And then frequency number 2 is going to be the next harmonic. So then therefore, if the first one had a value of N, the next harmonic will have a value of N plus 1. So, and now, just like I did in that standing waves problem, let's go ahead and just subtract one frequency from the other. So F2 minus F1. So F2 minus F1 is going to be this minus this, like so. And now let's go ahead and do the math. So when I do the math, I have here 440 minus 264, which is 176 hertz. And then on the right-hand side, we have NV over 2L minus NV over 2L, which drops out, and we're left with 1 times V over 2L. So V over 2L, remember, is the fundamental frequency of an open pipe. So if this organ pipe is an open pipe, then these guys here have to be multiples of 176. So now what I'll do is I'll take 176 and multiply it by 2. When I do, I don't get 264, nor do I get 440. Instead, I get 352 hertz, which is in between. If I take 176 hertz and multiply it by 3, then I get 528 hertz. That's in between 440 and 616, but it's neither of these two. So then therefore, this organ pipe cannot be an open pipe for this reason, because we're given that the organ pipe resonates at these frequencies, but nothing in between. So it's not an open pipe for that reason. Not an open pipe. So then therefore it must be a closed pipe. So if it's a closed pipe, then how do I find the fundamental frequency? Well, let's take this quantity here of 176 hertz, and let's divide it by 2. Because when I do, I'm taking the right-hand side of the expression and I'm dividing that by 2 as well, which is V over 4L, and that's the fundamental frequency of a closed pipe. Now, 176 divided by 2 is 88 hertz. So if the organ pipe is a closed pipe, then the frequencies that were given up on the top board, they have to be odd multiples of 88. So I'm going to take 88 and multiply it by 3. When I do, sure enough, I get 264 hertz. Let me take 88 and multiply it by 5. That then gives me 440 hertz. If I take 88 and multiply it by 7, that then gives me the other frequency of 616 hertz. So then therefore F1, F2, and F3 are odd multiples of 88 hertz. That is then therefore the answer to the problem. Part B of the problem asks, what is the fundamental frequency? It's this value here, okay? Okay, so this goes ahead now and it concludes part 2 of the lectures here on sound boxes. In addition to these lectures on sound boxes, you are also to take a look at the Beats demonstration for today, and also the Beats screencast for today as well. Today's shirt is Funebrarum. Be safe.